Okay, in this video we're going to have a look at when a function is differentiable. So a function is differentiable when you can differentiate it. Now I know that sounds very basic and obvious, but we need to make sure we get our terminology right. Okay, and in order to really get our heads around how this works, we need to remember what derivative is actually telling us. So a derivative function, f dash of x, gives the gradient of a tangent at any point on the graph of f of x. So if we've got this function here, okay, f of x, okay, well remember that f dash of x tells us the gradient at any point, the gradient of our tangent, sorry, at any point. So this would be at point A. Okay, so f dash of A tells us the gradient of this tangent. Okay, and we can draw tangents anywhere we like. Okay, it could be another one, and that's the whole point of being able to find f dash of x. Okay, is it tells us about the gradient of a tangent at any point on our graph. Okay, so now think about when we're going to run into trouble then, because really we care about when we can't find our derivative more than when we can, because the vast majority of the times we are going to be able to. Okay, so when can we run into problems? Okay, when the graph is not smooth. Okay, e.g. something like this, we're at a point. Okay, now if we think back to what our derivative is telling us, it's a gradient of a tangent at the point on our graph. Now anywhere here is fine, these are both straight lines, so anywhere along here is just going to be the gradient of our straight line. But the problem we've got here is at our point. Okay, so does my tangent go like this? Does my tangent go like this? My tangent go like this, or anything else? Okay? And the problem is we don't know. Okay, think of it's like our tangent is kind of like a seesaw on our curve. Normally it doesn't matter, it's only one point that we know that it's sort of pivoting at. Okay, but for here, okay, well it could be anywhere. Okay, so we can't actually find our derivative at a point that's not what we call smooth. Okay, so if it's not smooth, okay. Our other problem that we get is when a graph is not continuous. Okay, and we have the same sort of problem here. So I've got an example here, okay, where it's clearly not continuous. Now gradient is fine for this part and it's fine for this part, but again we run into problems at the end. Okay, now we include this point, okay, but where's my tangent go? Okay, even worse here, we don't include that point, so where's my tangent go? Okay, and in reality we don't know, and it causes us problems. Okay, now for this one we could have seen that our gradient was different values either side of this point. Okay, so this one was steeper than this one. Okay, so we had a different gradient for both sides of this, so that can be a hint there. Okay, a similar thing happened here, but if we're discontinuous like this, clearly we've got an asymptote here. Okay, well our derivative or our gradient of this function is actually going to be approaching the same thing, okay, on both sides, which is actually approaching infinity. Okay, so we're going to be getting bigger and bigger and bigger positive, and we're starting really positive here as well. Okay, so this is also going to cause us a problem. Okay, so I've got a little note here. So a function is said to be continuous, okay, at a point A if f of A exists. Okay, so we had problems here, okay, because f of A doesn't exist here. It did with this one, so I'll rub out those scribbles on it. Okay, this is point A. It exists at point A because we included here. Okay, so we've got no problems there. This one doesn't exist at this point. Okay, and the limit as x approaches A of f of x equals f of A. So that means that we've got to be approaching the value for f of A from both directions. Okay, so we're trying to, now it works for this one, okay, because we're approaching this value up here from both ways. Okay, but here it's not. From this way, we're approaching this value, okay, whatever that is, let's call that y1. Okay, but from the left, we're approaching this value down here, y2. Okay, so because we're approaching different values, okay, it doesn't work. Okay, now we can approach the same value and have it not work as well. If we had something like this. Okay, if we had a quadratic, okay, that didn't include a point up here. So as we approach this value A from this way, we're going to approach this y value. If we approach it this way, we're going to come along and we're going to approach it, but we're forgetting that the requirement that f of a exists. Because we're not including this value at a, f of a doesn't exist, therefore it's not continuous. Really easy way to remember continuous though is, can you draw the graph without taking your pen or pencil off the page? Okay, if you can't draw your graph without taking your pen or pencil off the page, it's not continuous. Okay, smooth can't be pointy. Okay, essentially is the idea. And our strict sense of smooth is we've got to have the same gradient from both sides. Okay, it's got to be smooth, we can't have any gaps. Okay, and you'll see that in some of the questions as well where we graph our derivative. Okay, so we're having a look at this one here for our example. Okay, we've got the rule f of x equals x squared plus 2x plus 1 when x is greater than or equal to 0, and x plus 1 when x is less than 0. We want to know when the derivative is defined, we want to find what the derivative is and sketch the derivative. Now it can be handy to start off with to actually sketch this to get an idea of what's happening. So if I look at this one, we can actually factorise that to be x plus 1 squared, which helps a fair bit because it tells us that we are a quadratic. Okay, so it touches here at -1. That'll mean it goes through this point here at 1. But this is only for when x is greater than or equal to 0. Okay, so we really just have this portion of graph here. Okay, that's going through 1. Now, when we're less than 0, right, we're actually a straight line coming through here, going through -1 as well. Okay, so it's looking like that. Okay, so we need to think then, well, what's actually happening here? Okay, and when is our derivative defined? Now, we can see we don't have any inherent problems with these two functions. Okay, they're continuous all the time. Okay, so our problem is going to be around here. Okay, and whether or not we're smooth and continuous. Okay, we are continuous, okay, because we are including all our points. Okay, so we're good there, but it's about whether or not we are smooth. Okay, and what we need to do for that is actually find what our derivative is for these. Okay, so if we actually find our derivative first, we say f dash of x, well, we've got to find our derivative for each part. So this is simply going to be 2x plus 2 for x is greater than or equal to 0, and this one is going to be 1, okay, for x is less than 0. Now if we sketch that, okay, we're going to see that 2x plus 2, that means we've come up by 2, okay, and then we've got a gradient of 2. So it's going to do something like that. This one, it's always just 1. So it's just a horizontal line. Okay, we're not including that one because we weren't including it here. And we've got that. Okay, now from there we can see, okay, that for each part our gradient isn't the same at 0. Okay, if it's not the same at 0, okay, that means that we're not smooth. That's what we've got there. So it's similar to our pointy situation. Okay, we included all our spots, okay, but our gradient isn't actually the same up here, it's different, okay, from one side to the other, and so that causes us problems, and that means that we're not smooth. So you hit the continuous requirement, bingo, we're fine there, but we're not smooth, okay, so we can't find our derivative at that point, okay, which is what we can do here. So we can essentially say that our derivative, okay, is defined for all real numbers excluding 0. Okay, it doesn't mean that we can't find our derivative. We did it quite successfully here, but what it means is it's not defined for that one value of 0. So hopefully that will help you get through the questions for this section.